Hi everyone. Today we're going to be looking at a study of a patient with a rheumatic mitral valve which exhibits both mitral stenosis and regurgitation. This is an initial parasternal long axis view of the heart, which shows a dilated ventricle and somewhat thickened mitral valve. The mitral valve thickness looks more prominent at the tips of the valve here than at the base. While the mitral valve does not open so well concomitantly, you see at the end during systole, there's a little gap here, which leads me to think that there may be an area of malcoaptation and subsequent mitral regurgitation. Measuring the end diastolic diameter, indeed it is quite large, measuring a distance of 58 millimeters. Moving on to color Doppler here, shows a large mitral regurgitation jet, the jet which extends to the posterior wall. When looking at a picture like this, make sure your Nyquist limit is set properly, not too low. Here it is at 60 centimeters per second, which is completely appropriate. Another thing to look at in the case of a mitral regurgitation study is to look at the severity of the tricuspid regurgitation and also to estimate what your pulmonary pressures are. This is the RV tilt view with the right ventricle up on top and the RA here on the bottom. You can see a fairly significant tricuspid regurgitation jet, the full extent of which we don't really see. We get the sense that it's not a truly severe tricuspid regurgitation jet given its parabolic rather than triangular shape. However, the tricuspid regurgitation velocity is quite large, measuring 357 centimeters per second. If you assume that the RA pressure were 5 millimeters of mercury, most likely it is higher, then you would get a pulmonary arterial systolic pressure of about 56 millimeters of mercury, which is severely elevated. Moving on to the short axis view of the heart, move on to the key images, which include here the mitral regurgitation on short axis, first without color, then with color. Regurgitation jet seen prominently here. So I'd like to collect images at this time in addition to looking at the pictures, so I can have the images consolidated in one place and I can do my calculations easily that way at the end. So before I do that, let's take one more look at the mitral valve. Color jet impressively looks severe and almost eccentric, with a jet hitting the posterior wall. You imagine if you were to Doppler this pulmonary vein over here, most likely you would get systolic pulmonary vein flow reversal. Okay. So the first image that we're going to get here is the mitral regurgitation jet CW to allow us to get the Vmax and the VTI to calculate our PISA, ERO by PISA, and our regurgitant volume. So here I'm trying to find the picture. Here we go. This is a CW across the mitral valve, so I'm going to go ahead and measure it. Where are we here? Mitral, my MR trace. Read down. We ignore the little hairs here. Now here, let's see if I can move this down. You can't see the full extent of the screen. However, the mitral mean velocity here is 392. VTI is 162.5 centimeters. Mean gradient, MR mean gradient, less important, so I won't mention that. So the key elements here is that the mitral valve VTI is 162 centimeters and the Vmax here is 577.8 centimeters per second. The next measurement we're going to get is the VTI of the PW across the LVOT. The reason we need to do this is to calculate the stroke volume so that we can eventually calculate the mitral regurgitant volume. So in order to calculate the stroke volume, we need two pieces of information. First is the VTI, here of the LVOT. And where are we here? LVOT trace. Here, 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 and here. Again, you can't really see this on my screen, but the VTI is 13, which is very small, 13 centimeters. Not so interested in the velocity here, but just to know it's quite low. Moving on. Annular size. The third piece of information that we want to get is the size of the LVOT, which here the tech has measured nicely for us, measuring 1.9 centimeters. So that and the VTI of the LVOT PW will now give us the stroke volume, which we can use later to calculate our regurgitant volume. These are jet gets. So now we turn to this image to get our PISA radius and aliasing velocity. Here the aliasing velocity is set at 30 centimeters per second. And what we're going to do is we're going to pause the image and find a place where we can accurately calculate a regurgitant, a PISA radius. I think this is a pretty good image. Again, you want to measure where the yellow meets the cyan, which is roughly about right here. Usually transthoracic pictures are not as pretty as this one. In this case, we get a PISA radius of 1.3 centimeters at a V aliasing of 30 centimeters per second. So we have all the pieces of information that we need to calculate a regurgitant orifice and a regurgitant volume and fraction for that matter. That is information regarding the mitral stenosis. In order to calculate and assess mitral stenosis, we will need to look at both the mean gradient and the pressure half time. Again, these are measurements that are heavily reliant on Doppler. And if your Doppler quality is suboptimal or you're not quite on angle with the jet, you can lead to some false calculations. That's why in the case of mitral stenosis, if you can get a transesophageal echocardiogram, or we're using 3D technology, get a effective opening area. It really is a gold standard for assessing mitral stenosis. But here is a CW across the mitral valve. What we're going to do is trace the mitral inflow right here. The tech does a pretty nice job here, but I think she is adding a little bit too much of the hairs. You definitely don't want to clip on all the hairs. So we get a mean gradient of 13 millimeters of mercury, which is severely elevated. Also, a gradient of 13.6 millimeters of mercury. So that's pretty elevated. If you're dealing with mitral stenosis, certainly that falls into the severe category. But just remember, your mean gradient can be elevated in both mitral regurgitation and stenosis. So in this case, we're obligated to look at our pressure half time to see if our pressure half time is long or short. If our pressure half time is short, i.e. under 130 milliseconds, this picture will be more consistent with a mitral regurgitation picture, causing such a large gradient across the mitral valve and diastole. So let's go ahead and do the pressure half time here. Right here. Down, down. Making sure you're getting the second half of the slope, which it's hard to see here, but I think here we have it. In any case, your mitral pressure half time is about 83 milliseconds, which is quite low. If you were to do run the equation of mitral valve area, which is 220 divided by the mitral valve pressure half time, you will get a area, let me just pull out my calculator here, of 2.6, which is not consistent with mitral stenosis at all. So I suspect that this patient has not very significant mitral stenosis and that the mean gradient is elevated, which is driven mostly by the mitral regurgitation severity. Next. Now we're going to talk about using the PISA method to get effective regurgitant orifice. So The PISA equation is 2 times pi times the PISA radius here, which is 1.3 centimeters, times the V alias and the V max. And if you were to use unit analysis, the 2 centimeters per second units will cancel out. So all you will have left in your answer is the unit, which is centimeters per second. If you think about it, effective regurgitant orifice is an area and hence should be in centimeters per second. So one thing I encourage my fellows to think about is using units and putting them units in your calculations and doing the calculations longhand. Don't shortcut yourself. Using unit analysis is a great way when you're taking your test or in everyday life to make sure you have the correct formula and you're doing the calculations correctly. And whenever you can, in most circumstances, when you're doing calculations, change all your units to centimeters per second. You don't want to be mixing any millimeters or meters in because that will really mess up your measurements. So using this formula, now we can make the appropriate substitutions and do the calculations. So 2 times pi, which we will just make here, 3.14, times the PISA radius, which we will change here to 1.3 centimeters squared. And what is 1.3 squared? 1.3 squared equals 1.69. So we can just change this to 1.69 centimeters squared. Okay. Times the V alias, which you can get here. Usually I set it around 30 to 35. 30 centimeters per second. And a V max, which we're going to get here. I know it's a little hard to see, but you're going to get 593 centimeters per second. 593 centimeters per second. So now let's pull up our calculator again and plug all these numbers in. 2 times 3.14 times 1.69 times 30 equals 318. Divide that by 593 centimeters per second. You get an effective regurgitant orifice of 0.53, which is actually quite large and consistent with severe mitral regurgitation. So let's put our number here. Or the number again, 0.53. We'll round up to 54. 0.54 centimeters squared. So now we're going to copy and paste and use that number to attain our regurgitant volume. So our regurgitant volume here is the ERO, which is this number here, multiplied by your mitral valve regurgitant VTI, which you get up here, 178. And 78 centimeters. Oops, typo. And just doing unit analysis here, your volume comes up to be centimeters cubed, which is appropriate for a volume. So going on over here, I had a chemistry teacher that was very much a stickler on significant figures, so we'll try to abide and not use this whole big number. So C 0.54 times 178. It comes out to a regurgitant volume of 96 centimeters cubed, or milliliters, which is, again. So next up, we're going to be calculating our stroke volume. So our stroke volume is calculated as LVOT VTI multiplied by LVOT area. So LVOT VTI, which is in centimeters here, is going to be 13 centimeters multiplied by our LVOT area. So our LVOT diameter is 1.9. So how are we going to do that? Remember, the area is going to be 1.9 divided by 2. That gives you the radius, 0.95 squared. 2 times pi. So pi r squared. And that will come out to be, pulling up our calculator, 0.95 times 0.95 equals 0.90 times pi, 3.14. And that gives you a LVOT area of 2.83. centimeters squared. So if we were to multiply these two together, 2.83 multiply by 13 centimeters, we will get a stroke volume that is actually super tiny, which is 35. Or 36? 36. Well, let's go up to 37. So you already see there's a huge problem where a regurgitant volume is significantly larger than a stroke volume. So plugging in these numbers, what was our regurgitant volume? All right, it was 96. So let's go to 96. 96 cm cubed divided by regurgitant volume, which is 96 cm cubed, plus stroke volume, which is 37 cm cubed. And what does this give us? First, let's work on the denominator. So 96 plus 37 equals. And then let's multiply that by 96. Oops, I think I did that wrong. Let me do that again. 96 plus 37 equals, okay, oh, I guess I was right. Multiply by 96. Then I'll give us 0.72, or 72% regurgitant. Oops, misspell that. Thank you, Google. So just to recap, our basic measurements are that the regurgitant orifice area is 0.54 centimeters squared. Our regurgitant volume is 96 centimeters cubed. And finally, our regurgitant fraction is 72%, all consistent with severe mitral regurgitation.